Hi everyone. Today I'm going to go over a few clarifications for Eevdf and go through an example. First, I wanted to define lag. So lag is defined in the paper as ideal service time minus real service time, meaning that a thread's lag is equivalent to the ideal service time it would have received in a fluid flow system minus the real service time it received in that time interval. We're going to go with this notation where it's ideal minus real. So that positive lag indicates that a thread should be scheduled earlier because it is owed time by the CPU, and negative lag means that the thread or task used up too much time and should be scheduled later on in the future. Okay, now let's go to these equations. So the best equations that you're going to use for Eevdf are actually this recurrence relation, where every thread that enters the system is initially going to be assigned a virtual eligible time equivalent to the current virtual time at which it enters. The virtual deadline is always going to be the virtual eligible time plus the request length for that request over W. For the purpose of simplicity, normally we're just going to say all of the request lengths are equal for one given thread. And yeah. Now, the next part of this equation is this recurrence relation. What does this mean? We're typically going to assume that a thread continuously submits requests for some number of requests. And for each subsequent request, we're updating the virtual eligible time for that new request to be the previous virtual deadline. There is one exception. Here, note that the virtual deadline of the previous request is using R, which is the request length of the thread. If the thread does not use R time units and instead uses U time units, instead of using equation 3, we're going to say, what would the deadline have been if I used U time units instead of R time units in equation 2? As in, what should the virtual deadline be given that I now know what the thread actually used for the previous request? This is visualized here. So I'm saying if the previous request received U time units of service instead of R time units of service for a given thread, I'm going to recalculate the next eligible time as the previous eligible time plus U over W, instead of just setting the new eligible time to the previous deadline. This is only when the thread used U time units instead of R time units. If we tell you that each thread used exactly the amount of time that it requested, then you're just going to follow this recurrence relation, and that is very important. Okay, so now let's go over this example. So we have two threads that are entering the system at different times. That's important. The first thread enters at time 0 and is alone for a whole time unit. For that one time unit, there's only one thread in the system, so the rate of virtual time is 1 over just thread's one weight, because it's the only thread in the system, so its weight is the total weight. So the rate of virtual time is 1 over 2, or 0.5. That means that after one time unit, we have 0.5 virtual time units. Now client 2 enters. The rate of virtual time is going to slow down. That indicates that there's more threads, there's more competition for the CPU. So each round, so to speak, of scheduling clients is going to slow down. It's going to take more time to give every client its turn now that we have more clients. So this is why when you look at the number line, it now is going to take 2 time units in real time to advance a half time unit in virtual time. Okay, that's kind of weirdly said. Let's look at whole numbers. So if my rate of virtual time is now 1/4, it's going to take me 4 real time units to advance a whole virtual time unit. Okay, if that didn't sink in, that's fine, because we're going to go slowly for these virtual time calculations. So the first thing that we do, okay, client 1, what is its virtual eligible time? the virtual time of the current real time at which it entered, which is just 0 because no time has passed. Client 2 enters at virtual time 0.5, so its virtual eligible time is 0.5. And what is its deadline? Its deadline for that request is going to be its eligible time, which we just said was 0.5, plus R over W, which in clients 2 case is 1 over 2. So its virtual deadline is 1 over 2 plus 1 over 2, which is 1. That's why we're getting this tuple of 0.5 comma 1 right where client 2 enters the system. That's saying that client 2's first eligible time is 0.5 and its first virtual deadline is 1. Note that all of these eligible times and deadlines that I'm calculating are in virtual time. Okay, so who do I schedule now? At any given time step, we're only going to consider eligible threads. Who is eligible? Both of them. Okay. Who has the earliest deadline? Well, both of them. So we're going to tie break. So let's say that client 2 runs. Now client 2 runs. Note that client 2 has used up its whole request. It's used up one time unit and it's only requesting one time unit per request. So now a new request begins. And as we said, we're going to assume that clients just continuously submit requests, one after another. Yeah. Okay, so after client 2 is done with one request, it needs to update its eligible time and deadline for the next request. So we're going to use the recurrence relation, and we know we can do that because client 2 requested R units, it used exactly R units, right? It didn't yield earlier, something like that. And so we update the virtual eligible time to be the previous deadline. So now VE is 1. And VD is going to be, again, 1 plus R over W, which is 1/2. So we get that VD is 1.5 for client 2. Client 1 has not been scheduled, so nothing changes to its virtual eligible time or deadline. Now, I want to note something very important. We are not using lag in the equations here. This is important because if you try and artificially use lag at every single time step for these equations specifically, they're not going to work. They incorporate lag under the assumption that each thread actually runs for R time units. So when you're updating the equations to consider U time units of service, if a thread only used U time units of service instead of R time units, you're basically accounting for lag in these equations. So TLDR, use the equations that we give you. Now, let's talk about lag because I didn't talk about it before. So let's look at the situation where client 1 enters. Client 1 enters and uses up one time unit. At that point in time, there's no other thread, so client 1 has the full weight of the CPU. So its ideal service time would just be one time unit and it received one time unit. Its lag is 0. Client 2 also starts off with 0 lag because it just entered the system. Now the next time unit is where it gets more interesting, or like the next quanta. Here we're also using quanta and time unit or tick interchangeably for simplicity. So starting at real time unit 1, client 2 gets to run for a whole time unit, and client 1 does not run during that time. If we're only looking at that one time step, client 2 got to run for one time unit. What is its ideal service time in a fluid flow system? Its ideal service time in a fluid flow system is going to be 1/2, which is its fractional share of the system. Its fractional share is just its own weight, which is 2, over the total weight of the system, which is 4. So its fractional share is 2 over 4. So client 2's fractional share is 2 over 4, which is 1/2. And that means that within one time unit in a fluid flow system, it would really only get 1/2 times 1 time units of service. So its ideal service time is 1/2, but it used up one whole time unit. That means that its lag is now negative 0.5. It is no longer eligible to get scheduled. Notice that this is taken into account when we're updating the virtual eligible time and deadline for that client because that client, when we update it, referring to client 2, is no longer eligible. We've updated its eligible time to 1 to indicate that it should not be run again until, um, you know, virtual time 1 rolls around. Okay, so I said the client 2's lag was zero point 0.5 if we're considering real time, or negative zero point 0.5, sorry. Client 1 is similarly entitled to 50% of the CPU because it has 50% of the weight. So client 1, during that time from 1 to 2, was entitled 1 full time unit, or sorry, 1 half time units, and it got to 0. So it has positive lag. It has 0.5 real time units of lag. So it should be eligible to be scheduled. We see that's also already incorporated in these eligible times and deadlines. Why is that? That's because we define the deadlines and eligible times based on the client's request length, and we are basically saying that a client can run or should be scheduled between a virtual eligible time and deadline that correspond somewhat to the starting time and finishing time of that client in a fluid flow system. The relationship to lag is a little bit more complicated, so I'm not going to spell it out in this video. But I have more information on my Notion page that I attached to the discussion 5 mega thread. I would also not worry too much about lag. If you can understand this example, then you should be good to go. So yeah. Also, I realize I didn't go through this entire example. So let's go through the rest of the example. Okay, so what had just happened? We scheduled client 2 from real time 1 to 2. Then client 2 became ineligible, and client 1 is the only one who's eligible at this point because we're at virtual time 0.75, and client 2's eligible time has been updated to be 1. So now let's run client 2. So client 2 gets to run, or sorry, now let's run client 1, who is the only one who's eligible. Client 1 is going to run, and now client 1's request has been serviced. Yay. So now we're going to update client 1's eligible time and deadline. Same thing, we look at the recurrence relation. Its next eligible time is the previous deadline. So its eligible time is 1. Its deadline is going to be 1 plus R over W, which is 1 plus 1, which is, so its deadline is 2. And now we have 2 threads who are both eligible, but client 2 has the earlier deadline. So client 2 is going to get scheduled. So note here that we're basically prioritizing threads with smaller request lengths and bigger weights and scheduling them first. In this case, the bigger weights doesn't really apply because they both have the same weights, but because the deadline is dictated by the request length and weight, if I have a higher weight, I have an earlier deadline, so I get more priority to be scheduled. I'm only scheduling threads that are eligible, and I'm choosing the one with the earliest deadline. Earliest eligible deadline first, or earliest eligible virtual deadline first. Okay, this video is kind of low quality. I didn't have that much time to edit it, so I apologize. Hopefully the Notion page is enough. I wouldn't worry too much about this as long as you understand, 1, what is virtual time? 2, how do I use this equation? And 3, how am I calculating these virtual times? What happens when a new thread enters the system? You are good. And just know not to use the lag from each time step in this recurrence relation because it's not going to work. Okay. My last note is that, as Matei said, the virtual lag is incorporated in the Linux scheduler as virtual time. As I was just describing it, I was talking about it in real time. We are not going to discuss how virtual lag is actually used because it's complicated, and as we just want you to get the general idea of how eligible times and deadlines are working. So let me know if you have any questions. Hopefully this was somewhat helpful. Again, apologize for it being pretty rushed, but yeah.